SightSense, a smart haptic alert obstacle detection system for the visually impaired. Hi, we are Group 5. My name is Anna Perez-Jarquin, and I'm an electrical engineer.
My name is Jasmine Abraham, and I'm an electrical engineer.
Hello, my name is Giovanni Garces, and I am a photonic sciences engineer.
Hi, my name is Johan Johnson, and I'm a computer engineering major.
Our demo highlights include object detection and distortion analysis, real-time obstacle capabilities, and alert and haptic feedback system. For our overall system, the first key engineering requirement was achieving high detection accuracy, meaning the device can recognize different types of obstacles like people, walls, curbs, and steps with at least 90% accuracy. Next, we set a detection range of up to 2 meters in front of the user. This distance gives enough time for the system to alert the user before getting too close to an obstacle. Finally, since real-time feedback is critical, our system needed an immediate response time of under 250 milliseconds. This ensures that once an obstacle is detected, the alert, whether through vibration or sound, happens almost instantly, helping the user react quickly and safely. SightSense design. In our design, we focused on creating a system that could detect obstacles accurately while remaining comfortable and practical for the user. The sensors are positioned on the front of the shin guard to provide a clear and reliable detection range, while the vibration motor and speaker deliver real-time feedback through haptic and audio alerts. Our final prototype will be mounted on the shin guard, allowing the system to stay secure, lightweight, and easy to wear. The ESP32S3 runs the full detection process, activating vibration for close obstacles and audio cues for objects detected farther away. Overall, this design keeps the system compact, efficient, and ready for everyday use.
Optical setup. This is a 3D print of our setup for our optical system. The basics are going to be the 650 nanometer red laser, the first lens, second lens, and diffractive optical element, and this is what will create our gridded pattern. For the optical design setup used to create the structured light pattern, we start with the 3-volt power supply to the 650 nanometer 50 milliwatt output laser, as well as 2 lenses, one being a 6mm focal length and the 68mm focal length, as well as the diffractive optical element to create the pattern. We are using an optical band pass filter from the camera, roughly from 630 to 670 nanometer, which is why we chose the 650 nanometer red laser. For our optical setup, we are using a 40-degree tilt to be able to project the gridded light pattern on the ground. The height that we will be testing at will be 26 inches from the ground. We will be using an optical band pass filter to filter out the bandwidth between 630 and 670 nanometer. The images below show the difference in the optical bandpass filter versus without the optical bandpass filter for the camera.
Electrical setup.
In this video, we are showing how all of our PCBs are connected. We can see a big main board connects all the components and PCBs together, starting with the ultrasonic sensors, the 3.3 volt regulator, the 5 volt moving up to our audio amplifier and speaker, the LCD screen, our vibration motor and driver, and underneath we have our ESP32S3 room, which is connected.
Optics testing. For the obstacle detection testing, we have set up in the Creole Senior Design Lab. We have added a 3-volt battery to the 3D print for the optical setup. We have added a 40-degree tilt, and we will be testing the obstacle detection at 2 meters. Here we are showing our testing for our obstacle detection at 2 meters. We are placing an object at 2 meters away from the user, removing the object and placing it back 5 times. Each time the neural network caught distortion in the gridded pattern. And
Machine learning. Neural network for obstacle detection. This section shows how the object detection model was developed and trained using edge impulse. We began by collecting and labeling 530 images that captured both distortion and non-distortion conditions in the projected grid pattern. Each image was carefully tagged to help the model learn the difference between a clean, flat projection and one that's warped by an obstacle or change in depth. During training, the model's accuracy reached about 99.97% with the validation F1 score of roughly 0.74 for distorted frames. This means it was highly reliable at recognizing when grid lines were bent or broken while minimizing false positives. Once training was complete, the model was deployed through a QR code which allowed instant testing on a phone. By scanning the code, the model ran directly in the browser using the phone's camera, classifying each frame in real time as either distorted or not distorted. These results confirmed that our edge impulse not only performs with exceptional accuracy, but also runs efficiently on portable hardware. In this demonstration, the object is placed directly within the grid projection at a distance of about 2 meters. As soon as the object enters a frame, you can see the grid pattern distort and the F1 score on screen immediately rise to indicate a successful detection. When the object is removed, the grid returns to its normal shape and the detection drops back down to 0, showing the model's responsiveness in real time. This consistency demonstrates that the edge impulse model can reliably recognize when an object is present or removed, even from a distance of 2 meters, validating its precision and stability for real-world applications.
The next trial run that we are demonstrating is on the second floor of the Creole building. We are showing a user approaching the stairs and showing how the neural network is being able to detect distortion, allowing the user to know that he is approaching a drop-off at the stairs. We again did 5 trial runs where we showed successful deployment of the neural network.
In this demonstration, the grid projection is directed toward a lower surface to simulate a step down or drop off. As the projection crosses the edge, the grid lines begin to distort and separate, signaling a change in depth. The object detection model identifies these distortions instantly, and the F1 score updates on screen to reflect the detection confidence. This strong performance shows that the system can accurately recognize downward terrain changes, even under variations in lighting or surface texture. By maintaining real-time responsiveness and high precision, the edge impulse model demonstrates consistent reliability in detecting potential trip hazards and elevation drops, a key function for the Sight Smart Shoe system.
The next trial run that we are demonstrating will be between the first and second floor in the Creole building, where we are showing that as the user is approaching the stairs, the neural network will be able to detect the first step and allow the user to know that there is an object there or step. And again, we showed 5 trial runs where the neural network successfully detected the stairs.
In this demonstration, you can see the projected grid approaching a raised surface, representing a step-up obstacle. As the grid reaches the edge, subtle distortions appear in the pattern, which the model identifies in real time. When the distortion is detected, the F1 score value updates on screen, showing the model's confidence in that frame. Overall, the system consistently recognized the upward step, confirming that our edge impulse model can reliably detect elevation changes in real-world environments.
The next demonstration that we will present will be outside when the user will encounter a ditch or drop-off. Here we successfully demonstrate that as the user approaches the ditch, the neural network successfully identifies the drop-off and will let the user know that there is a drop-off or ditch and to find another path.
In this demonstration, the grid projection is directed over a small ditch to test the system's ability to recognize sudden drops in terrain. As the grid passes over the recessed area, the line stretches and breaks apart, a clear sign of depth distortion. The object detection model immediately registers this change, and the F1 score value on screen increases as the system identifies the ditch. When the grid moves back onto level ground, the pattern restabilizes, and the F1 score returns to baseline. Across multiple tests, the model maintains strong and consistent accuracy, confirming its ability to detect depression or holes that may pose a tripping hazard.
Overall PCB testing and implementation. In this photo, you can see how we measured the ultrasonic sensors. We did this in 3 installments, 0 to 0.5 meters, 0.5 to 1 meter, and 1 meter to 2 meters.
For the midterm trials, we are currently running the code on an Arduino board while we work on fixing a transfer issue with our main PCB. The main board powers on and connects fine, but it isn't uploading the code yet. Aside from that, all 5 of our other PCBs are working and able to transfer code successfully. For this test, we used a distance-based code that reads from 2 ultrasonic sensors, one from the left and one from the right. The LCD displays both distances in meters and in inches in real time. Depending on how close an object gets, the vibration and speaker respond differently. In the far range, there is no sound. In the mid-range, a lower beep plays, and in the close range, a higher tone activates as well as a vibration motor. This confirms that both the speaker and vibration feedback react correctly.
This is the second trial for our testing. Notice how the ultrasonic sensors detect an obstacle and will produce a sound using the speaker and a vibration using the vibration motor when it is present. Listen to the beeps and vibrations carefully.
For our third trial, we focused on improving the audio alert system. We tested two frequency ranges, 600 Hz for mid-range obstacles and 1000 Hz for close-range obstacles. This helped us create a clearer distinction between distance levels, making it easier for users to recognize how close an obstacle is just by the sound. Here, we're demonstrating the vibration feedback that activates at close range. As the user approaches an obstacle, once the distance goes below half a meter, the vibration motor kicks in to give an immediate physical alert. This feature is especially useful in noisy environments where the audio cues might not be as noticeable. By combining both vibration and sound, we're making the system more intuitive and reliable for quick obstacle awareness. Data from trials.
In this section, we present the results from our object detection and system testing for the Sight Smart Shoe. Our goal was to evaluate how accurately the model could detect obstacles at various distances and terrain changes. Specifically, a flat obstacle at 1 meter, a step up, and a step down. For the 1 meter obstacle detection scenario, the system achieved F1 scores ranging from 0.78 to 0.98, with a calculated mean of 0.89 and a standard deviation of 0.07. These results indicate a very consistent, accurate detection performance when obstacles are directly ahead at a fixed distance. For the step up test, F1 scores range from 0.54 to 0.88, resulting in a mean of 0.71 and a standard deviation of 0.14. The higher variation here reflects the added challenge of vertical elevation changes where lighting and grid distortions vary more significantly between runs. In the step-down trials, F1 scores range from 0.71 to 0.96, with a mean of 0.84 and a standard deviation of 0.12. While slightly less consistent than the 1 meter test, the overall accuracy remains strong, showing that the system reliably detects downward slopes and declines. On the validation set, the model achieved an accuracy of 99.97%, and on the test set, about 99.74. For the distorted class specifically, the precision reached 0.62, recall 0.92, and F1 score 0.74 during validation, while maintaining similar performance on testing. Overall, the macro F1 score was around 0.87, confirming excellent classification balance between distorted and background frames.
Our close range testing for our ultrasonic sensors show a 0.3 meter standard deviation or 3 centimeters deviation. This is the ideal. It means that we don't have many outliers and there are a few tweaks that we can make in our code to correct these issues, but truly our accuracy is where we would like it to be. Our ultrasonic sensor results for our mid-range testing, or 0.5 to 0.75 meters, has a standard deviation of 0.04 meters or 4 centimeters. We are quite happy with this accuracy rating because it shows that there's only about 4 centimeters difference on our measuring. This means that with a little bit more tweaking in code, we should be able to get that lower. However, it is not necessary. For our ultrasonic sensor results for our far range testing, we can see a standard deviation of about 0.28 meters or 28 centimeters. Since we're measuring at about 2 meters to 0 meters, we would like to decrease this number significantly to get the most accurate range. With a little bit more programming, we should be able to accomplish this.
This slide shows our audio and vibration feedback test results. We ran 10 trials at different distances to see when each alert activates. For objects farther than 0.75 meters, the system stays silent. Between 0.5 and 0.75 meters, we used a 600 Hz beep to indicate a mid-range obstacle, and when the distance dropped below 0.5 meters, the 1000 Hz tone played along with the vibration motor turning on. As you can see from runs 7 through 10, the vibration consistently triggered at close range, confirming that both the audio and haptic feedback work together for reliable detection. This slide summarizes our overall system performance. We evaluated the ultrasonic sensors at short, mid, and long ranges, and all readings stayed within our 5% error tolerance. The average measured distances were about 0.33 meters for short range, 0.55 meters for mid-range, and 1.54 meters for long range, each meeting the target criteria. For feedback, the audio successfully differentiated between the 600 Hz and 1000 Hz zones, and the vibration motor consistently activated only at close range, below half a meter. Overall, all tests passed, confirming that our system performs accurately and reliably across all detection zones. Remaining tasks for our project. For the optics, We're focusing on improving daytime outdoor performance to make sure detection works reliably under different lighting conditions. We also plan to deploy the final code on the ESP32 cam so all components run together as one system. Finally, we'll conduct additional model training to further improve detection accuracy. On the electrical side, we'll transfer and verify the full system code on our ESP32S3 PCB for complete functionality. The prototype will then be mounted onto the shin guard for integrated testing. We're also enhancing the feedback system by adding voice alerts that indicate obstacle distance and increasing the vibration motor strength. Once these steps are complete, we'll run final testing and finish updating all project documentation. And that concludes our midterm demo. Thank you for your time.